So today it's my pleasure to introduce Professor Karen Dahlman. Professor Dahlman received her PhD from Cornell University. She was a junior fellow at Harvard University before joining the faculty here in 1999, almost 20 years. And her research on soft condensed matter physics connected many subfields of physics and demonstrated how truly universal is the law of universality. And she has received numerous awards throughout her career and was recently awarded the prestigious Guggenheim Fellowship. So let's welcome Professor Dahlman.
Thank you for the kind introduction. And thank you for coming on a Saturday morning so we can tell you a little bit about what we've been doing. What I'm going to do is I'm going to give you an overview over the things that we work on. And we are looking for input and ideas for other systems where you could apply some of these things. So if anything you see reminds you of something you've worked with or you come across, we're always interested. So I should say the work that I'm going to be talking about has been mostly done by our students. So we have undergraduate students that do fantastic work taking experimental data and analyzing it, and then they work with our graduate students that develop the models together, and then they compare them both. And so if any of the kids here are interested in being an undergrad in the future, we'd love to have you. If you're interested in research, come to us, knock on our doors, and we are always looking for people to help us. So there were a number, basically I'm a condensed matter theorist, so that means we work on modeling things, and there have been a lot of groups that have experimental groups all over the country that have been kind enough to give us their data. And as I'm going to go through the talk, I'll show you which group gave us which data. And so I want to highlight, so the model that I'm going to talk to you about has been developed with Yehuda Ben-Zion and Jonathan Ewell. So Yehuda Ben-Zion is an earth scientist, and Jonathan Ewell is a chemical engineer, and I'm a physicist, so it's a very interdisciplinary work. And then our graduate students, especially Jim Antonaglia, has done a lot of the work I'm going to show you today. He's now a grad student in Michigan. And then our graduate students, especially Michael LeBlanc, he graduated, and he is now actually doing working in finance. So he's applying all of these ideas of avalanches to the stock market, and he's soon going to be really rich. And then we have several collaborations here at Illinois with Richard Weaver, who has a background in astrophysics. You'll see that at the end of the talk. And Michael Weissman, I don't know, he may have talked before here. He does very nice work on magnetic systems and systems with avalanches, Nigel Goldenfeld and Martin Ostoja-Starzewski. You might know these people. And then there have been several groups at Caltech and here at Illinois and at Duke University that gave us the data, but I'll show you as we go through who gave us which data. So the question we are studying is avalanches and crackling noise. So if you take a piece of metal and you bend it, you might think, you know, if I would take here this piece of metal and I would bend it, you might think there's nothing crackling there. It's a smooth deformation. But if you look up close, or if you had a really strong microphone, you would actually hear it crackle. So there's lots of systems that crackle or that have avalanches. So if I talk about avalanches, most people think about snow avalanches. That is one example where something happens on a mountain, you kick it, and then there's a snow avalanche going down the mountain. That's an avalanche. When I say avalanche, I mean anything that's like a cascade, you know, sort of like a domino effect. If you take a wooden stick and you bend it, it tends to crackle because there's fibers. You know, one fiber may break and it triggers another one. You get an avalanche of fiber breaking. There are these metals. You've seen them up there. Nitinol is one of them. That's an alloy of nickel and titanium. And then there's others that have more components. They actually have this feature. They crackle quite loudly when you amplify the noise. You couldn't hear it out there, but they do crackle loudly. And they have this interesting feature that I just mentioned it on the side. This is not really something we've been working on, but it's just neat about them. When some of you have seen it up there, when you have You can see that up there, right? Here's the wire. It's been bent out of shape. But then if you heat it up, so let's see if I can get this done. Erica set this up so nicely. I can only break it. So if you heat it up, then it deforms, and actually it goes back to its original shape. So originally it was, more or less like this. If I would keep going, it would stretch out even more. But they're called shape memory alloys, these memory wires. They remember their original shape when you heat them up. The way it does it is actually pretty easy if you're interested. Okay, why don't I just say a couple words about that? You have in these wires, you have these atoms arranged in little unit cells. And at low temperatures, the unit cells, they're sort of at the corners of rectangles, if you want to say. And they can be a rectangle like this, or they can be a rectangle that's more shaped like this. They could be in rectangles like that. And so when you deform it, you can basically switch a rectangle that's oriented this way to a rectangle that's oriented this way. You're basically pushing the boundary between horizontal rectangles and vertical rectangles around in your material. But if you heat it up, then all these unit cells become squares. So there's only one shape it can go back to. That's why it remembers it. So that's sort of just a rough idea of what's going on. And they are used, for example, when people have problems with, are in danger of getting a heart attack. Sometimes people put in stents. What they do is they take these shape memory alloys, they crumple them, make them really small, put them in the artery, and then when they get heated up to the body temperature, they unfold to the shape that they were taught, which is just right to open up the artery. So that's where they're used in medicine. We have been using them more because they crackle. We're interested in this crackling noise. So I'll show you more about that later. So that's one example. Another example of avalanches are Rice Krispies. So every morning for breakfast, you have your Rice Krispies, right? When you pour milk over them, it crackles, and I think it sounds something like this, just to remind you. Let's see, where is it? There. Sounds familiar? Yeah. So these are avalanches of milk getting into the pores of your Rice Krispies. So it might go into one pore, and then it goes into another pore, so you get sort of these avalanches of milk invading your Rice Krispies. Another example is neuronal avalanches in the brain. So we study that actually right now. Here's the thing. We have, in our brain, there are neurons, and they tend to fire in avalanches. So one neuron might fire, give a little voltage pulse, and that gets transported to another neuron, triggers that to fire also. So you can get a cascade of neuron firings. Now in the morning, these avalanches are really small, and I can totally identify with that. But in the middle of the day, you get avalanches that are broadly distributed. You get a lot of small ones and a few big ones. And in the evening, when you stay up too late, then they can actually go through the entire brain. And actually, that's what happens in epileptic seizures. So if you stay up too late, you can get seizures. So don't stay up too late. But basically, throughout the day, the statistics of these avalanches changes. And the optimal state is where in the middle of the day, where you have lots of small ones and a few big ones. So we're working on why this is optimal for the brain. And then when you sleep, the synapses and all the connections in your brain get reset, and in the morning it starts all over again. So there's a lot of questions as to why the brain does this and what that's good for. Another example of avalanches is if you take a magnet. So in a magnet, if you would zoom in, magnets have, you can think of magnets or, iron. Let's say if you think of iron, you can think of it as something like you have here lots of little compass needles. And if you apply a magnetic field, so this is a bar magnet, and you hold it next to it, then they tend to align. Yeah, right? You see that? Now, if I reverse the field, so if I put my magnetic field here to the other side, then you see how they switch over. They try to, they adjust to it. And they do that in avalanches. So you do it back here. See, there you get avalanches of these spins following the field. And we have studied that in great detail. So it turns out if you have a lot of disorder in homogeneity in your magnet, then these avalanches tend to be small. And if you make it very uniform, they can get very large. And in the middle, there's sort of this critical point where it can't quite decide, so it gets you avalanches of all sizes. And so we had published this, and then there were people in the social sciences that read that, and they said, whoa, this is interesting. Let's use this for decision making. So imagine you have these little compass needles, and a needle pointing in one direction is like a yes decision, and a compass needle pointing in the other direction is like a no decision. Here you are, and you're talking to your neighbor, and you all would like to agree, so you talk him really a lot, and then finally, okay, I agree with you. He changes his direction. Then he goes off and talks to his neighbor and convinces him. So you can get avalanches of decisions that are changed. And so a model like this would say if you have a very inhomogeneous situation, the avalanches stay mostly small. But if it's very homogeneous, you can get huge avalanches going through the entire system. And so that's useful for lots of things. So some people called us up that work on power grids, for example. You can have in power grids avalanches of blackouts. And so you would like these avalanches to stay small. Yep?
How are you defining an avalanche?
Okay, good question. So an avalanche, I really mean something like a domino effect. In these dominoes, that something, something starts it and it triggers something else. So something that's like a cascade. So in this case, I would say when I put my magnet here, maybe the spins here might decide to flip, but then they, because they flip, they're coupled to the next ones, and then they tell them you also flip. So I really mean with avalanche something that's like a cascading effect. It starts somewhere that kicks this, like a chain reaction. That's really what I mean.
So a small initial.
Exactly.
Trigger something large.
Exactly right. You have a small initial kick, and then because they're all coupled to each other, that starts this chain reaction. Exactly right. Like a domino effect. Yeah, I'm glad you asked that. That's exactly right. Yeah. Anyway, yeah.
And in social science, you said it would be peer pressure.
Yeah, peer pressure, exactly. That's right. And TV, that could be like the magnetic field that may change things, maybe. So that's right, exactly. So they're basically trying to see how communities make decisions. Exactly, peer pressure would be a good one. Yep, that would be the coupling. Yeah, any other questions so far? Yep. So maybe so there's other systems in superconductors here in our department, Eduardo Fratkin and Dale von Harlingen, who was our department head until just a few months ago, and Mike Weissman and Laura Green. They have all worked on superconductors. So there you can also see avalanches. You have sort of little vortices that move in avalanches. I won't have time to go into that. Probably the most famous example are earthquakes. So you see here, I'm plotting here, the size of an earthquake versus time. These are the earthquakes from 1995, measured. I think these were from all over the world. And you see you have lots of small ones, and a few big ones every now and then. And so now I'm going to get to this plot here. So let me use the pointer, that's better. This plot here. This will come back over and over again, so I really want to make this as clear as I can. This is a plot of the number of earthquakes versus their size. So it's really a histogram. And this is for these earthquakes that were observed in 1995. And you see you have lots of small ones and a few big ones, and all the sizes in between. And they follow a regular law. On this plot, this is called a log-log plot. It's a straight line, and the slope of that line, basically the incline, that is a number that is called universal, which what that means is it's the same if you look at the earthquakes in California or the earthquakes in China or Japan or Israel, you know, it's always pretty much the same number. It doesn't depend on where you look. So basically the incline of that slope here, so that you know, I mean, basically, yeah, the slope of this blue line here is the same all over. So basically that tells you sort of the ratio from small to large is pretty much the same all over. And the question is, why is that? You know, why? So, yep. We'll get into that in more detail. Are there any questions on this plot, what this plot means? So really what they do is they plot here how many magnitude 3 or 4 we get, how many magnitude 5 we get, how many magnitude 6, and so on. That's all that is. Okay. So these are just examples of systems with avalanches. And here's the big open questions in the field. So what we would like to know is how many systems behave the same way on long length scales that are large compared to the microscopic details. So that means if I look at a system, you know, I really don't care about the details. I just want to sort of get the big picture. How many of these systems behave the same way? The reason why we're interested in that is because we want to know whether we can transfer results from one system to another. So, for example, can we use lab experiments to understand earthquakes? That would be nice. So for a while, there were people in experiments that did, people in labs, they did rock experiments. They would take a chunk of rock, and they would slowly compress it, and then would notice that this compression goes in steps. And then they would say, well, does that have ever anything to do with earthquakes? You know, in earthquakes, you have this earthquake fault. So maybe let me draw this. Put the chalk. Thank you. Yes, thank you very much. If you have an earthquake fault, you know, here's the surface of the Earth. Here's an earthquake fault, like this. You know, maybe here's a tree. You know, there. No building. And then, so what happens is in an earthquake, this continent over here may move this way, and this one moves this way. And then here's your earthquake fault. Let's say, you know, I'll make a grid because we're physicists, so we just want to know what's going on. So you shear it, and then you have little patches here slipping forward. And if this one slips, you know, it might trigger another one to slip. So you get an avalanche of, you know, it's basically like a cascade of these little patches moving forward in a little jump. So what we have here a little demonstration, and I think Erica will help us put this on the screen, I guess. But basically what we've done here is imagine you would flip this over just because of geometry. So now it's like this, you know, here's your tree, you know, and here's the other side. This moves this way, and this moves this way. So you pull it, and you watch what's happening here on the fault. That's basically. This is sort of just to show you how people started modeling earthquakes. They said, well, you know, this is one side of the ground, this is the other side, and now if I just slowly pull this, you see like one of them might, let me do this from the other side here. So one of them may slip. It worked better earlier. But you can see, you know, one block may move, and because it's connected to the next one with a spring, you know, this one may move, stuck, right? You know, that's why for a long time you don't see anything. And then eventually you get this cascade of little patches slipping. And that's what happens in earthquakes. So that's why we think of earthquakes as also being an avalanche. Anyways, so the question was, can we, to come back to here, this list, we want to know, can we transfer results from one system to another? That's why we need to know how universal are these things. Then another question is, can we predict the statistics of this noise? That would be very useful. For example, if you want to reduce it. So for example, we were called by LIGO. That's a group that wants to measure gravitational waves. And they have to have super sensitive measurement instruments. They have these huge mirrors, you know, that are, and they have wires that connect things, and it has to be so super precise because the signal is so small. The problem is these wires, every now and then they would crackle, and that would mess up their measurement. So they called us up and said, what can we do to reduce that? So for that, we need to know, can we predict this crackling, and can we somehow do something to suppress it, to make these big avalanches of big slips in the material to make them smaller? Or another example is, another important question is, does a crackling noise tell us when a material will break? And that's how we want to raise our funding. For example, think of it, you're sitting in an airplane and you're wondering, you know, is that wing going to fall off or not? So if you could tap on it and listen to the crackling noise and tell from that how close it is to breaking, that would be useful. So basically, we want to use this to test materials. We want to bend them and listen to them and say, oh, okay, not this one. Let's use the other one. Or can you predict the lifetime of a material? Can you say, you know, sometimes, you know, things get weaker if they have been bent back and forth many times. You know that with a wire, you go eeky, eeky, and eventually it breaks, right? So the question is, if you've had, you know, such a piece of metal that has been exposed to deformation a lot, can you listen to the crackling and say, oh, yeah, we should switch it out and have a new one? Another example where this is useful is for precursors to large earthquakes. That would be very nice if we could really understand the statistics of earthquakes to say something about when the big one is really coming. So far, we can't. We cannot predict it. There's some debates going on, but in California they have the center where all the groups that have programs that you know are built to predict earthquakes submit their programs, and then their results are being compared to the data as it comes in. And so far nobody can really predict the earthquakes, and so that's an open question. What about landslides? That's another example of these avalanches. You know, it'd be nice if you could tell, especially in California, you get always these landslides when there's heavy rain. It'd be nice to predict where it's going to happen, when it's going to happen, so you can evacuate. And I already mentioned blackouts to power grids. And here is another example where it's really important to make progress. We would like to predict epileptic seizures. It'd be nice if you could monitor what's going on in the brain. If you know, oh, an epileptic seizure is about to happen, maybe you could prevent it before it actually gets there. So that also is an open question. Another one, we're not working on this, otherwise I wouldn't be here. But it would be nice if you could predict stock market crashes from just the statistics. So a stock market crash is another example of an avalanche. Something happens and then it spreads out. And then there's other questions as to creep, you know, materials. Let's say if you have some metal with some load on it, you know, it slowly creeps. It'd be nice if you could predict what happens. And we're always interested in any types of data or observations that allow us to sort of test our models for that. So what I'm going to do is I'm just very quickly show you a very simple model we've been using that gives you a flavor of the types of models we use for this. And then I'm going to show you comparison of the results to crystals, metals, granular materials, earthquakes, and if we have time, also a little bit to stars. And then we have a conclusion. So the model, we have, basically we wanted to understand the deformation of materials and the crackling that you have there. And of course you can simulate it, but that takes a lot of time. So we wanted something simple, back of the envelope kind of thing, to get an intuition for what's going on. And so we have the simple model. It just has one parameter, which we call the weakening. I may say a few words about that. And it makes prediction for slip sizes. That means like the avalanche sizes, how long they take, and then sort of the power spectra of acoustic emission. That means sort of the noise that you hear in acoustic emission. For brittle materials, those are the ones that snap. For ductile ones, those are the ones that, you know, sort of deform and they don't really snap. And hardening materials, those are metals. I don't know, you may have heard about work hardening, when you take a piece of copper and you bend it out of shape, and then if you try to bend it back, it's so much harder. So people people use that for horseshoes, for example. This feature of hardening, when people used to make horseshoes, they would shape the horseshoe and then they would bang on it. That would introduce a lot of what we call dislocations, so the defects in the material, and those defects would get entangled, and then it was much harder to deform that metal than it was initially. So those are called hardening materials, and copper, for example, is such a hardening material. So basically, these types of, any of these materials, for those, we can sort of look at the crackling noise, and the simple model has something to say about the statistics of that, of the crackling noise in there. And we have predictions that agree with first experiments, and then we're always looking for more experiments. So here's the idea of this simple model. You say, you say any chunk of material will have weak spots in it, right? Some spots are a little weaker than others. You can't see the weak spots, but they're in there. It's not completely uniform. So in this piece of metal, we'll have some weak spots in it. And then if you bend it, then we say you have these little weak spots. Let's say, here's a little picture of a zoom in. This might be a zoom in into a metal. And let's say here's a little weak spot, but if you bend it there, we call that a dislocation. It's a little defect in the crystal structure. And that's where the material is particularly weak. And so if you push here, such a weak spot can just move through the material, meaning at a weak spot, you can have a little slip. But if it slips there, it can trigger the neighboring patch to also slip. And then you get a slip avalanche, very similar to what I showed with this thing. You sort of get a slip avalanche going through the material. And so this little cartoon is supposed to show that. You're saying, here's a weak spot. When it changes color, it slips. And then it's connected by springs, if you like. It's coupled through the elastic interaction to the neighboring weak spots, and then they slip also, and they can trigger another one and another one. So you get a cascade. So imagine at each of those patches where it changes color, it slipped. And so that's how you get a slip cascade or slip avalanche. And what I'm drawing here is the number of weak spots slipping as a function of time. So it starts with one weak spot slipping here. One slips, that triggers 2, triggers 3, triggers 1, and then the avalanche stops. So this would be sort of the slip velocity, or if you like, you could think of it that way, how fast the slip propagates as a function of time. That would sort of, if you think of it in terms of earthquakes, it would give you a time profile of how the earthquake propagates. It slips fast, and maybe it speeds up more, and eventually it slows down again, and then it stops. So basically, long story short, the whole idea that goes into the model is we're saying any material has weak spots, and they're coupled, with springs, just like here. They're coupled with these springs, and so if one slips, it triggers others to slip, and that gives us a slip avalanche. Yep?
So can we say why it gets larger and then smaller? Maybe you just did say that, but there's a lot.
I didn't say that, actually. It's a very good question. Yes. So the reason, actually, why sometimes it's larger or smaller is because we assume, I don't know, I think that's on the next slide. Yeah. So basically, we say that each of these weak spots has sort of a threshold when it slips. And we say that threshold is randomly distributed throughout the material. So, in some places it's low, in some other places it's higher. So, in some regions may be surrounded with some other regions where the threshold is a little higher, so then the slip avalanche can't get very far. And in other cases, there may be a larger region with low thresholds, so then the avalanches can get bigger. That's sort of the idea. So
then getting small again, because it already sort of moved in all the spots with the low threshold, and so you run out of...
Yes, that's another reason. Exactly. If it's already moved, exactly, then it takes a while before it gets reloaded again. Exactly right. Exactly right. So you basically already explained this new slide here. Basically what we say, it's true. Basically what we say is, here's on this axis is the stress versus time, and when we say the force increases with which you push until you hit the threshold, so it's basically stuck, and then when it reaches the threshold, it slips, and then by some random amount, that relaxes it right there, just like you said, and then it resticks again. And then the threshold has to, the force has to be loaded up again till it can slip again. So it gets loaded again, and if it hits that critical force again with which you have to push, then it can slip again. So it's very much like in this example here. I really had to push quite a bit until this thing finally decided to move. and then it moved, and then it was relaxed a little bit, and then I have to push again before I can get it to move again. That's the whole idea. So now, and then when something slips, because it slips, it pushes the neighbor. So basically the force, there's an increasing force to the neighboring ones, redistributed, and so it can trigger them to slip as well. So you get a slip avalanche. Now we say, I told you this model had one tuning parameter, which we call the weakening. That's saying that sometimes things can get easier to slip after they slipped once. So for example, imagine in an earthquake, if you have slipped, if where it slipped, if it dilated a little bit, the two surfaces maybe got apart a little bit, it would be easier to slip again a second time. So that's what we call the weakening. So in brittle material, no, not now. So the weakening is basically telling you that after it slipped, it got weaker. Cracks do that also. It may have cracked, so after there's a crack, it's so much easier to slip again. So brittle materials, the ones that snap, they have a lot of weakening. Or hardening, it could get harder to slip again. That's what happens in the horseshoe. After you deformed it, it gets much harder to deform it again. I won't say much about hardening. So I thought every physics talk has to have one equation. so I just put one equation just for fun. What we're saying there is, I guess I could switch back to the, I forgot how to do this. I guess I have to go HDMI. And then left projector, is that right? Perfect. All right. Okay, thank you, Erica. What would we do without you? So here's the idea is that the slip velocity, as you shear it, the slip velocity, how much it deforms, is proportional to the applied force or stress, if you like, plus some interaction. That's the coupling, the effect of the springs between the patches, and then plus some pinning. That's what that means, is some random force that sort of models the heterogeneity throughout the material. But really, this is just saying the same thing as we just saw in that picture, just in formula. So there's nothing new here. It turns out that the interaction between these so basically the coupling between these weak spots is long-ranged. So it turns out actually that if this guy slips here forward, then throughout, imagine there's all this material on either side, all connected by springs. So through that, this guy actually feels it, even if the guy in the middle doesn't jump also. So long story short, in statistical physics, we have these beautiful tools that allow us to basically take a model like this and then to zoom out, to look at it, to basically get the big picture, the behavior on long length scales that are much larger than these individual weak spots. So we zoom out and look at it from far away. And then that tells us that if we make that a simple approximation, which is called mean field theory, which is sort of saying every spot is coupled to everything else, that gives us exact results. What that means is we can just solve it with pencil and paper. That's all I'm saying. So we don't have to simulate. We can just do a pencil and paper calculation and predict what this model is going to do. And so now I'm going to show you what the model does. So if you plot the force with which you push, so you have here your, imagine you have here your piece of material and you push with a certain force. And so on the y-axis, I'm plotting the force with which I push. And here on this axis, we plot what we call the strain. That's really the amount of deformation that you get. So you push, push, push. Then the way this material will behave, or this model behaves, is it tells you as you push harder, it deforms more. And then eventually you reach some critical force where this material just, I wrote breaks, but really what it does is, if it's a ductile material, copper or something, you push on this pillar, and eventually it turns into a pancake. So it can't sustain the load anymore. And so if you zoom in, if you look up close, the model says there should be little steps. What that means is the deformation is going forward in steps, just like when you step on a Coke can. It's not smooth. It's a jerky deformation. And then you can calculate how big these steps are, and you can calculate how many big ones and how many small ones you get, and then you get this power distribution, and the slope is 1.5. The model predicts that without any fitting parameter. It just comes right out. So that was the model. So then the model says, the other thing is, and this comes back to where our funding comes from, it says that at small stresses, these steps should be small. But as you push harder, they should get really big. Now, when we saw that, we were really happy, because that means if you push harder, the crackling gets louder. So that's useful. So that means, really, when you listen, you know, that airplane wing, when you listen, if it's really loud, that could be a problem, you know, when it cracks. I guess we should have known this up front. But we can now say how much louder it can get, you know, if it gets really bad. So that's very useful, that this crackling strength changes with the amount of force you apply. So then there's lots of predictions. So our grad students worked really hard. They cranked out all these predictions. So we had now all these predictions from the model. So Jonathan Yule, who is this chemical engineer and really down to earth, he said, well, enough with the theory. Does it actually work? So we thought, all right, let's look at this. So the model, I told you, has no information about the length scale we're working at or the spatial structure. All we said is there's weak spots that are coupled. So we might as well compare it to experiments on different scales, small ones or large ones. So now I'm going to show you the experiments. So first I went to Caltech and talked to Julia Greer there, and they have tiny, tiny crystals. They're nanocrystals. She tells me they're so small, when she puts them on a table and she sneezes, they don't move. They're really small. And so what they do is they take them and they compress them. So I'm going to show you a movie from their lab. So here is, this comes with sound effects. So as you compress them, you see, this is a little pillar. You compress them, and you see that the deformation is not smooth. It's very jerky. And you see in the upper left-hand corner, you see this plot of the force versus the displacement, and you see it has all these jumps that we saw in the model also. So when she showed us this, we said, oh, this is great. We have a model that shows these same curves with these jumps that I showed you earlier, and the statistics, and we like to compare. And she said, this is great because we have all this data and we don't know what to do with it. So they gave us the data, and Nir Friedman, who was a grad student in our group at the time, he took it and he analyzed it. And remember how I told you that the model says that the avalanches should get bigger, the steps should get bigger as you approach failure? So in a histogram, when you plot the number of avalanches versus their size, that means that the maximum avalanche size, you know, where that ends, should grow as you go to higher forces or higher stresses, as you push harder. That was the prediction from the model, and this was the data. It looks just like it. And then the model said, oh, if you rescale the axes, you know, stretch them in a certain way, these curves should all collapse on top of each other, and it predicted the function. And so Nir did that, and he found it all worked just exactly like the model said. So we thought, okay, great. These tiny crystals are described by this very, very simple-minded model, really. So then we thought, well, okay, that was on the nanometer scale. What about bigger scale? What about millimeter scale? There were two groups. There was Todd Hufnagel and Wendelin Wright. So Todd is at Johns Hopkins University. Wendelin Wright is at Bucknell University. They worked together. They did nice experiments on metals with amorphous structure. Amorphous structure means the atoms are not in a neat crystal, but they're kind of randomly distributed throughout. They're just in random places. They're not in neat rows at all. And they work basically, they're called bulk metallic glasses. Just for information, bulk metallic glasses, they got a lot of press lately. So Apple bought all the patents for those metals because they want to make cell phone casings out of them. They have this feature. There's some nice videos online if you just Google bulk metallic glasses, where they have a ball of bulk metallic glass and they let it drop and it just bounces forever. It doesn't stop, you know, it just keeps going. So there's very little dissipation in there, just keeps going. It's so for small forces, it's incredibly elastic. It doesn't deform. Only when you put really big forces on it, then it shatters like glass. So it's kind of weird. It's a metal, though. So it's a very strange, it's an alloy out of different components, different metals. Anyways, so they take small samples, millimeter-sized samples, they compress them, and again, they see that the deformation curve is jerky. In these cases, the avalanches are drops in this curve, in this deformation versus time curve. The reason is they drove it a little differently. They just pushed at a fixed speed, and so every drop means every avalanche gives them a drop in the stress. It's a long story short, but basically the vertical drops, those are your avalanches. Anyways, I'll make a long story very short because I don't have time. Basically, we looked at the statistics of these avalanches. The dashed lines are the predictions for the red parts of the data, and as long as they're parallel, we're good. So in each of the cases, so we looked at the size distribution, and we looked at how long these avalanches take, and how fast they are, and we looked at the acoustic emission. In all of these cases that we looked at, it always agreed with the simple model. We also looked, remember that little movie I showed you in the beginning that showed you like 1 weak spot triggers 2, triggers 3, triggers 1, and then the avalanche stops? Well, in this experiment, they collected 100,000 data points in a second, very fast. So they could watch individual slips, and they could actually see how fast is that avalanche propagating. And our model says that the small avalanches should have, if you plot the velocity versus time, should have a profile like this, and the larger ones like this. And then it says if you rescale them, they should fall on top of each other, and the dashed line here is the predicted curve from the model, and it worked. So basically, this was just another way of testing the model, and it worked. It agreed with the model. So now we think these Bach metallic glasses also obey this simple model. Again, there were some other experiments by Peter Leo at Tennessee. Actually, this is from Junwei Chao in China, and he sent us the data. They collaborate with the Tennessee group. Basically, there again, as they push harder, the avalanches get bigger. In the data, you get the same thing. You can do the same collapse as I showed you in the crystals, and it seems to work again. So these are all just examples to show you that the data agrees with the model predictions. So there's lots of predictions from the model that agreed with the data. So we think for these Bach metallic glasses, the model really gets it right. It does describe what happens. So then we thought, okay, let's go to a bigger scale. What about on a meter scale? Let's look at granular materials, sandbox, something like that. So there's different groups that did beautiful experiments. Bob Berenger at Duke, and Bob Ecke at Los Alamos National Lab, and also Dmitry Denisov and Peter Schall at Amsterdam. They did different experiments. Here's an experiment from Bob Berenger's lab at Duke. They have a little Couette cell. What this is you have these little grains in here, lots of little beads, and if they get squeezed, they light up. Really what it is, it's photoelastic discs, and they put them through cross polarizers. But long story short, whenever you see something light up, that means there were some beads there that were squeezed. You have this inner wheel that rotates, and then you build up these force chains, and then there's a slip in there somewhere, and that relaxes that whole region. That's why they don't light up anymore. And then the wheel keeps turning, and those force chains build up again, and until there's again a slip, and then it relaxes again. So they had beautiful data of this, and they looked at the statistics of these avalanches, and again, it agreed with the model. So they also had a different geometry. They had a geometry like this. I should mention, for grains, you can also pack them more densely. We have a different version of the model where you can study it as a function of how densely you pack the grain. That also agreed with what they saw when they packed them more densely. So then they had this geometry here, and they gave us the data. Again, this is the number of avalanches versus their size. And our model said it should follow the slope here. And so we drew that slope on top of the data, and it agreed. And the same for the duration. All we did is we just drew the predicted slope on top of it, and it fell right on top of the data. So we thought, okay, maybe for these granular data, it also works. There was another experiment at Los Alamos. They were interested in earthquakes. So this is their experiment that they had on earthquakes. Imagine this is supposed to be your earthquake fault here. This is one side of the fault. This is the other side. And they move one fault, one side versus the other. And then they see slips in this earthquake fault. And they measured the size again. And again, this is the predicted slope, this triangle here. And this is drawn on top of the data. And it looked reasonably okay, within the right ballpark. And then, oops, I missed. Oh, okay. I can just tell you there was another experiment which we were really excited about from Peter Schall in Amsterdam, where they had a three-dimensional shear cell, so really like a three-dimensional block, and they sheared it. And long story short, it agreed also with the data, with the model predictions. So then what about earthquakes? That's really actually how we started working on this. We were interested in earthquakes. So this is, the scale of that is much bigger. This could be, the faults can be hundreds of kilometers long for earthquakes. The San Andreas fault is incredibly long. So what we did is first we had this model and we actually simulated it. So I'll show you here a simulation. This, by the way, is LA. Here's the earthquake fault, and then you see down here the earthquakes as basically you slowly shear the continents, and then you see you get lots of small earthquakes. Sometimes a little bigger, sometimes a little smaller, and every now and then you get a really big one. But thankfully they're there. They don't happen very often. So that's the nice thing of this power law. You have fewer big ones and small ones. And so then remember how for the Bach metallic glasses I told you about how the velocity versus time, how that profile looks, and how that agreed with the model prediction? Well, we tried that in 2006 for earthquake data, but there weren't enough earthquakes. So we didn't have very good comparison. But then since then, there have been more earthquakes, and the group at Caltech, Menendrin Maya and Tom Heaton and John Paul Amporero, they were able to get their hands on data from subduction zones. Those are when one continent goes underneath another one. So then you get very large earthquakes, and they had beautiful data on that. And they plotted that. This is the data, again, velocity versus time. And then the dashed line is the prediction from this very simple model I told you about. And it falls right on top of the data. So now this is on earthquake scale. So basically, again, for earthquakes, it's right to say it's just weak spots that are coupled, and that's how you can understand them. Very much like in these lab experiments on these millimeter scale samples on Bach metallic glasses that we looked at. So if you compare the results across scales, you have here the number of earthquakes versus their size. This was our model predicted slope, this 3/2. And here you see the nanocrystal data next to the amorphous data, and this is your earthquake data. They all have basically the same slope. That was the prediction of the model that it should come on, plus other predictions that I don't have time to go into. So we can say more about how the maximum size scales with the force. But so we sent that in, and then someone said, oh, wait, you need more experiments. So we added the granular data and the rocks on different scales. So this shows you nanocrystals at 10 to the -9 meters, all the way to earthquakes, where you get into much larger scales. And we plotted them on top of each other. This was the predicted slope, and these are all these different systems: nanocrystals, Bach metallic glasses, rocks, and granular materials and earthquakes. And they follow this predicted slope. And then we did the scaling collapse. Remember how earlier I told you if you push harder, the avalanches get bigger, and that you then could rescale the axis to collapse it? Well, we did that for all of them. And then this gray line is the predicted curve plotted on top of the data. This is all to say that we think in each of these systems you get the same behavior, that you have weak spots that are coupled. Basically, that's what you learned from this. So then you might ask, why does it work? And then you can talk about that, yeah, there's this way of, if you take models for different systems and you zoom out, that's called the renormalization group, you zoom out, that if you look on long length scales, all these different models, when you zoom out, they start to behave the same way. And so basically, as long as you look on scales that are large compared to the microscopic details, so you don't look on scales where you see every single atom, but you zoom out, then the model for Bach metallic glasses and for earthquakes on long length scales, they behave the same way. So I already told you that you can apply this to biology for neurons in the brain. that's a little different. And then just to finish up, okay, I just wanted to mention for the brain, basically you get very similar distributions for your avalanches. And then to finish up, I just wanted to mention the last thing that's really fun, that we're having fun with right now. So we worked on this, and Richard Weaver, who is here in the department, he came to us, and he said, have you heard of Tabby Star? So you may have read in the popular press, Tabby Star is a star in our galaxy, and it flickers. So every now and then it gets really dark. And there were lots of theories. Why? Why does it do that? You know, the sun doesn't seem to go this dark, you know, every now and then. So why does this star do this? Other stars also don't seem to get that dark. And our favorite theory out there was that there's extraterrestrials. And they have built a structure around the star. And so every now and then that structure gets between us and the star, and that's why it looks so dark. So that was where the field was at. And so he was saying, have you looked at that with these tools? And you know, we didn't know what we were going to get into, but we said we can try. And so we basically analyzed the statistics of these flickers. And it turns out they have just the same statistics as we see in this plastic deformation. I don't know if I included that. Yes, so see, if you look at the sizes of these dimming events, they again follow a power law. You know, it's basically plotted the same way as what I showed you before. And you get the same types of statistics. And you get the same types of, remember those functions I showed you for the bulk metallic glasses? Well, these dimming events have those same functions. So we're wondering, could there be a similar process going on? We don't know what it is. We don't think it's plastic deformation, but it could be something like this. You know, there could be maybe magnetic fields that play a role. We know that this is a star with a strong magnetic field. We're working on it. We don't know. That's an open question. And then we look at other stars. And some of them have a smaller cutoff. You know, they get a power law with a smaller cutoff. And other ones have a bigger cutoff, very much like what I showed you earlier in the plastic deformation when I said when you're at low stresses, you have small avalanches, and at higher stresses, you get bigger avalanches. It seemed here that some stars had smaller avalanches and other ones bigger ones. And you could, in the same way as we did for the plasticity, we could rescale these axes and collapse it. So we're thinking maybe this Tabby star is near some kind of phase transition. We know near phase transitions, you get big fluctuations. Things fluctuate a lot. But we honestly don't know. So we're looking for new students to come and help us with that. So yeah. So maybe just to finish, so you've seen some examples of avalanches, and we're always interested in other examples. So if this reminds you of anything you've seen or something, or data you've seen, or observations, or anything, we'd always love to hear about it. But it gives you a feel for how you can get away with very simple models to get an intuition for what's going on. And I should stop there. Thank you very much.
Questions back there?
Yes, several years ago, I had a stress fracture in a little bone in my foot.
Yes.
Now, that thing has been annoying me for several years. And
Yes.
I had worn one of those neoprene bandage things and would compress it, and then it wouldn't hurt.
Oh, great.
I had to work outside, walk, and things like that.
Yes.
Anyway, eventually, it was so painful, they x-rayed and said, well, you have a stress fracture. It's like going like this, and then, yeah, and then it broke. And so then I had to wear a foot.
Oh,
One of those boot things for some time. I was just wondering, since this took a period of time to develop,
yes.
maybe if I had worn that neoprene bandage on there more to compress everything, perhaps it would never have broken. Have you done anything with bones?
Great question. Great question. Excellent. You are spot on. So first, to answer your question, I think you're right. As you compress it, you know, if it opens up, you have a lot of stress concentration near the tip of a crack, and that causes it to grow. So compressing it is a great remedy. You're exactly right. And on bones, wow, you're ahead of it, the whole thing. We have been talking to Ivona Jaziuk here in the mechanical engineering. Oh, there she is. Okay, so she does right next to you. Actually, you should talk to her. Yes, so she does beautiful experiments breaking bones. So you should talk to her. We exactly right. We would that's where we're going next. So she knows all about it. You should talk to her. Yes, very good question.
So we have there.
Yeah.
Famous breaking of the spaghetti, where you try to break it in 2 pieces,
Yes.
and it breaks instead into 3. I wonder if this would be relevant for that.
Oh, okay, interesting. That's a very good question. What's that?
When large smokestacks, when they fall over, they don't just break in half, they break into 3 pieces.
Very interesting. Yes, I think that depends on how you load it. We haven't looked at that, but we should. I agree. No, I absolutely agree. We haven't looked at that. But I absolutely agree. It's very much related to this. Yes, it depends also how you load it. So, so far we have not done much with bending tests yet. Bending tests would be like when you bend it like this, because then the loading condition is not uniform throughout. We should though, because that in a lot of applications that comes up. So very good point. Yep, I'll remember that. We should look more into that. Good question. Mm-hmm. Yeah.
Yeah, I've noticed that your experiments, you seem to apply pressure in only one direction.
Yes.
What happens if you apply pressure simultaneously in 2 different directions? Does that complicate your equations?
Good question. It does. It does. Yes, it does complicate it. Yes. Okay, you actually opened a can of worms. So we have so simplified it by only like looking in one direction. The reason is because then we can solve it analytically. As soon as you have 2 directions, it actually gets so complicated. I think then we would probably have to simulate it because I'm not sure if we can still do it with pencil paper in that case.
When math gets so complicated, you can't do it.
Yes, we wanted to start with a simple case first, but which is not to say for applications, I think the directional dependence will, for lots of applications, that is important. We wanted to first sort of get the main idea just to see if it even works, if you can get away with the simple picture of weak spots coupled. But I think for applications, yes, I think, but the general idea should still work, I think, because you still have weak spots.
The reason I ask is I remember in college I used to stand on, soda cans.
Yeah.
And they hold my weight, and then I just tap them on the side, and they collapse.
Oh, that's what you mean. Okay. Well, in that case, I think you started an avalanche because you push here, and if you tap it on the side, you basically kick it more. You basically tell it start the avalanche over here. You basically have given it made this spot where you tapped it a little weaker by pushing it already in. So that way you have started the avalanche. You've given it a kick at one point, and then it decides, okay, that's where I'm going to deform, and then it deforms
Would
off.
that be applicable to, say, like earthquake slippage? It's under pressure, it's fine until something taps it?
Yes, absolutely. Very good question. So, for example, the Earth's crust is under tremendous stress everywhere throughout. So when people dig a lake anywhere and fill it with water, so for example, when they dig for coal, then they have always these things, and then later they fill it with water. Usually earthquakes start right there where you put the water in, because you've put in some extra load with that water, the weight of the water right there, and then you get little earthquakes right there. So it is absolutely right. Or for example, the fracking, is another example where you locally put some stress on, and then that is enough to trigger your earthquakes. Yeah. So that's a very similar case. Very good point. Yes. Yeah. Thanks for mentioning that. That's good. Mm-hmm.
Okay. One final question.
Okay, yeah, back to the airplane wing and similar problems. You said that, when it gets loud, you should worry.
Yeah.
So how do you know how loud is loud enough? And
Yes.
One thing I was wondering is, obviously the small events, there's a lot more of them. They fit the curves better.
Yes.
At the low end of things, because it's a large number of events.
Yes.
At the top end,
Yes.
Small number of events, that's often where it doesn't fit the curve as well, because they're so. Can one actually do predictions from that when the actual noise spectrum diverts from the prediction? Does that indicate that you're near the critical point?
Yes, good question. So actually, I didn't say this, but I don't know. I always lose that chalk. That tail end, actually, I didn't talk about it. The model actually makes a prediction for that too. It's actually a power law multiplied with an exponential. So you're exactly right. When it starts entering that, once it starts looking more like an exponential, then we know we're at the maximum avalanche size. So you're spot on. That's exactly right. Yep, good point. Mm-hmm.
Okay, yeah, so Karen will stay longer if you have questions.
Yeah,
you can
yeah,
come down.
absolutely.
So let's thank her again.